So I already started this last time actually. So what we're going to do is we're going to look at determinants, right? And we're going to look at determinants, but through three axioms. Okay. So normally determinant is given as a formula, right? Here what we're going to do is we're going to say that there are three axioms that a determinant function must satisfy, and then we'll show that this uniquely specifies the determinant. Okay. So you've all seen determinants before, right? Okay. Okay, so what we're going to do is, so let's just start with the definition. So the definition here says that you consider any function det from n cross n to to f, right? An n cross n matrix to a number, and we're going to restrict to the field being either real or complex. So mostly just think of it as complex and things. Right? Okay, so there were three properties. So let's quickly review them. The first property is normalization. Okay, so this says, so what is the definition saying? So we're going to say a function det. Okay, so a function det is a determinant. If the following are true. Okay. So we're just saying what the properties are. The first property is normalization. So what is normalization? Normalization says that the determinant of I, the identity matrix, should be 1. The determinant of identity should be 1, right? The second property is anti-symmetry. So we have A is an n cross n matrix, okay? And suppose A prime is A with 2 rows swapped. Okay? So you have 2 matrices, A and A prime. You just have the 2 matrices, the rows are swapped. Then the requirement is that determinant of A should be the same as minus of determinant of A. Is this okay? Anti-symmetry making sense? What's the name? K? That was K, right? K? What's his name? A. K. Sorry, I'm just going to use the initial, okay? Is it making sense? Okay, let me know, okay, if something's not clear. Okay. So this is anti-symmetry. And then the third property is linearity in row. Okay, this is a very important property, and let's make sure we understand this. So linearity in each row. What does this mean? It means that, so what we're going to do is, so write down A as some matrix, okay? So it is written as a bunch of rows, okay? So this is some matrix A. Now what we're going to do is, we want to compute, so when we write determinant of A, we are going to use the notation det of V1, Vn. Okay, this is just notation. All I'm doing is, instead of writing A, I'm writing the list of row vectors. Is that right? Okay. So the property is the following. So we want det of, okay, so consider A, and then you should also consider U. Okay, so U is another row vector, some arbitrary row vector. Okay, I mean, obviously the size has to match, but otherwise it's arbitrary. Okay? So the determinant of V1, so the first and the last entries are the same. The only thing you change is the kth entry. Okay, so it's the same as the A matrix, except in the kth row, what you're doing is you're replacing Vk with, so replace Vk with C1 Ck plus C2 U. Okay. So let me write it down properly again. Sorry, give me a sec. Determinant of V1 all the way to Vk minus 1. So these entries, these rows are the same. Okay? And in the next row you have C1, Vk, C1 times Vk plus C2 times U. So you've taken a linear combination of the rows at the kth entry. Everything else is the same. Okay? So this is the kth entry, and then you have vk plus 1, so on. Okay, vn. So the determinant of this object must be the same as the determinant of the original matrix times C1 plus C2 times determinant of the same matrix with the kth row replaced with U. Is it making sense? Is that okay? Sure? Okay? Doesn't have to. Yeah, it's arbitrary. So U is arbitrary. Okay, so the question was, does U have to be one of these? And the answer is no. It's arbitrary. Okay? Fine? Making sense? Okay, so now, making space would be a little bit more challenging in this one. Okay, great. So, okay, so last time what we did was we also looked at, we looked at our usual definition. So, okay, so let me write it down. So last time, we checked some of these properties. Okay, using our formula for the 2x2 and 3x3 case. Okay, so we checked some of them, we verified them that this sort of makes sense. So for example, one of the trivial things you can check is that, of course, the formula is this, like for 2x2 case, it's AD minus BC. So it's easy to check that the determinant of 1, 1, oh sorry. So what would this be? This 1, right? This is 1. And then what is the determinant of 0, 1, 1, 0? Minus 1, right? So this is basically saying you should swap the rows, you pick a minus 1. Sort of works in general. Because it's not hard to check the property. So that is not really the interesting thing. The interesting thing is that that using those properties, so what we want to show is, I'll tell you what the overall objective here in this section is. So the goal here is to show that using those three axioms, okay, one can show that det is uniquely specified. Okay? So the formula that we learned will be a consequence of these definitions. So we'll see that there is no other formula that could potentially satisfy this. Okay, that is sort of the main approach. Okay, so let's see. There are a few small things that are worth noting. Okay, so first of all, before we move on, okay, so let me say another thing. So how are we going to do it? So the approach is that we'll first prove some properties. So first we'll prove some properties. Okay, which are like consequences of the axiom. The second part I'm going to leave as homework. Okay, so here we sort of apply the proof strategy on 2x2 and 3x3. So 2x2 and 3x3. Okay, this we will skip because the general argument is actually much more clear. Okay, the third is the general argument, the general formula. Okay, so we'll derive the formula explicitly, just starting from the axioms, and that means it's unique, right? Because we just derive it as a consequence. Okay. So we may or may not do this. I plan to skip it. So let's see how much time. Okay, so let's begin then. Here are some important things to sort of keep in mind. Okay, because I'm sure already know this, but determinant of A is not the same as A plus B is not the same as determinant of A plus determinant of. Okay. This is something that's like you can find very simple counter examples. I leave it as homework to cook up a counter example. Of course, you need the formula, so you can use like 2x2 or 3x3. You can do it. Okay. Another thing that looks kind of plausible is the determinant of TA. So we said, right, that it's linear in the rows. So you might think if you multiply the entire matrix with T, that would also give you t times det, the determinant of the matrix, is not true. Okay, because the actual thing is n. Okay, this is sort of the important thing. Okay. So now let's look at some nice properties of this consequence of this definition. Okay, so here it's just saying that let det be as in definition 1 that we just saw. Then det satisfies the following. Okay, so the first is that if any two rows of A are equal, then the determinant vanishes. Okay, why is that? Swap. Exactly. Right, so this one is immediate. Why? Because of the antisymmetric property. The antisymmetric property said that if you swap any two rows, you pick up a minus n. Okay, and if two rows are identical and you swap them, you get the same matrix. Right? So therefore, determinant of A would be equal to determinant of minus n. So therefore it is. Okay, so we will eliminate it out quickly. So this is because, suppose, say you have V1 to Vn. Okay, this is your matrix A. Right? I'm just writing it as a sequence of, let me write it like this. So determinant of V1, VL, say VL and VM are the ones that are the same. Okay, and you have n many, and there are matrices in between. The determinant of this thing is going to be the same as minus of determinant of V1 all the way, and you swap this, right? VM, VL, and Vn. Correct? And because VL is the same as Vm, right? No, suppose VL equals Vm, right? Because VL, Vm are the same, that would mean that determinant of A is the same as minus determinant of A, which is 0, which implies determinant of A is good. It's completely trivial, okay? Nothing complicated. So let's now look at the next step. So the next property says the following. Just making some space. Give me a second. Great. The next property says if A has a 0 row, then the determinant of A is 0. Okay, how do we do this? I also know to let's see. So it says that okay, so suppose Vk is the all 0. I think I remember now. You want to think about it for a second? Maybe it's easier rather than me telling you. Exactly. Okay, so what is the statement? It is saying that if A has any 0 row at all, then the determinant will vanish. Okay, why is that? Because as S pointed out, so if you take, so the third axiom, so axiom 3 said what? It was about linear combination, right? And we know and love linear combinations because whenever you see a 0, it means things become 0. Right? So what does the linear combination say? It says that, so if you have the determinant of some matrix, it has a bunch of, suppose the nth row is the one that was 0, right? Vn. So you can write this as the determinant of V1 all the way is 0 times VL, right? And then Vn again, correct? You can do that. And then this would mean what? I can pull out the 0, right? Because of linearity. It's linear in the rows, right? Okay. So therefore this thing is 0. And that's what we're doing. Okay. So assume VL. Is that okay? Any questions? Making sense? Okay. Is it making sense? Okay. One. So that's the second property. The third property says that if the rows of A are linearly independent, then linearly dependent, not independent, linearly dependent, then determinant of A is 0. This is the third property. Says if rows of A are linearly dependent, then determinant of A is So, okay, so why is that? Let's see. It's also going to use the linear combination property. So, right. So let's say without loss of generality, suppose V1 can be written as a linear combination of the remaining proofs. So CI, is that right? So from this step, it should already start looking like where the proof is going. Right? Because what are we going to use? We're going to use linearity and the fact that the moment you have two rows being the same, the thing disappears. Right? So let's see how we write it formally. So determinant of V we can write as determinant of V1 to Vn, correct? And this we can write as determinant of. So we're going to substitute for V1 this expression over here, and we will get sum over I. But crucially, the index is going from 2 onwards. Yes, it's 2 to 1, Ci Vi, and then you have V2 and so on. Okay. Right. Now this I can pull out because of linearity, the summation. So I pull out the summation, and I will have Ci Vi, V2 equals to V. Okay. Now what can you say about? I forgot to write determinant. What can you say about the determinant of this matrix? Yeah, you can pull out C. That's fine. That is true. Let's also pull out C. That's true. Right? Give it. Okay. So we pull out Ci as well, which we could do. Okay. So now what can you say about this matrix? The determinant. Exactly. Okay. So what can you say about this matrix? Exactly. There will always be at least one row, two rows that are the same, right? So always there will always be two rows that are identical. Yeah. So therefore this will be 0. Okay. Any question? Completely straightforward. Very nice. So now let's look at property 4. Actually, I've also written down the property in the proof itself. So let's look at the fourth property right here. So the fourth property says that adding or subtracting a multiple of one row from another leaves the determinant unchanged. Okay. So adding, subtracting multiple of one row from another leaves the determinant unchanged. You can read it, or is it too small? Can you read? Is the font okay? Determinant unchanged. Okay, why is that? So let's take a simple example. Okay, so suppose what we'll do is we'll add. Okay, so suppose the matrix is V1 to Vn. Exactly. Let's suppose we're writing this determinant. Okay, and suppose we add, say, the nth row to the first row. Okay, you can also write it more generally. I'm just for basically telling you the idea. You have the proof. So you would have V1 plus VL. Correct? We want to know whether they're equal or not, right? Of course, I can't just assume what we want to prove. So we want to check whether it matches, right? Okay. So what property can we use here? So we can use linearity, right? Linearity in the first row. To write this as what? We can write it as determinant of V1, VL, Vn plus determinant of VL, it's correct. VL, Vn. Is that okay? Making sense? Okay, and then what can you say about this one? Has two rows the same. Great. So it vanishes. Yeah? So this is same. So you're done? Reasonable? Okay. Yeah? Making sense? Okay. Very good. And okay, so now you can generalize this idea, right? So here you could have added coefficients. Right, so since you can add, if I had added, so let's say if I added some coefficient c over here, so let me make it faster. Sorry. I guess if I had added c in addition to the coefficient, what would that have changed? It would have pulled out c over here. Correct. So even if you take linear combination with some rows, it won't make a difference. The statement will still be true. You can add more rows if you want. Is that okay? Okay. Is it okay? Like, all I'm saying is you can add coefficients. It doesn't make a difference. Okay, and then you can add more rows. That is also fine. So the entire argument is true. Okay, so this establishes the fact that you can add, subtract multiples of another row. It doesn't. Okay. Right. Now we're going to look at. So the fifth part, there were two statements. Well, there was one statement, but it was written as two statements. Sorry, we are going to write it as two statements. So it says the following. So it says that the determinant of a diagonal matrix is equal to the product of the diagonal entries. Okay. Now this is not something that we postulated. Right? This is just following from the definitions themselves. Okay. So the statement is the determinant of a diagonal matrix equals the product of its diagonal entries. And this is also coming from linearity, right? Because what we are going to do is, so let's imagine you have a matrix. So let's see how to do this. Right? So suppose A1 to AN is your matrix. Okay, zeros everywhere else, right? We want to compute the determinant of this object. The determinant of this. Oh, I should also mention that sometimes I write just this to mean the determinant. Okay, that is just notation. These are equal. Okay, like the straight lines is just notation. Don't get confused. So when I write determinant of A1 to AN, okay, so here, what is the first thing I can do? I can pull out the coefficient A1 using axiom 3. Right, so this will be equal to A1 times determinant of 1, A2, and A. You see where I'm going with this? Yeah? So what would be the next step? A1 times A2, and then determinant of 1, 1, A3, and so on. Correct? So this will give you A1, A2 all the way to AN, and then determinant of 1, 1, 1. Right, and what is the determinant of the odd one matrix? Axiom 1 property, normalization. Okay. So this thing is. Any questions? Any sense? Okay. Fantastic. Now let's look at the B part of the same property. I think this property from the set 5. Okay. So you see, it's kind of really just following from linearity. Like as we saw it in linear algebra, like lots of things follow from just assuming linearity. Okay. So now 5b is saying the following. It's saying something similar but for triangular matrices. Okay, so it says, so let me read the statement. It says the determinant of a triangular matrix equals the product of the diagonal entries. Okay. So remember there was also this theorem when you were doing complex matrices and things that said what? It said that if you have an upper triangular matrix or a lower triangular matrix, the diagonal entries give you the eigenvalues. Okay. And here look, the determinant is turning out to also be the product of the diagonal entries of an upper and lower triangle. So maybe there is some relation with eigenvalues. Okay, so we'll see. Okay. So right, so what are we saying? So the statement is the determinant of an upper triangular matrix equals the product of diagonal entries. Okay. So how do we see this? Okay, so let's start with the diagonal matrix. Upper triangular matrix. Because for lower triangular, the argument is the same. Nothing really changes. Okay. So A1, 2, and so on. A2, 2. This is a matrix. A1n, A2n, all the way to A. Okay, and then these ones are zeros. Okay, these are zeros. Okay. All right. So now we want to compute the determinant of this matrix. So determinant of Yeah, I'm going to be a little bit lazy and just erase things and write determinant of this matrix. Okay, so we want to compute the determinant of this matrix. One thing we can do, okay, this is very similar to when we were doing row reduction. Okay, so now what we're going to do is we're going to employ the same idea. We're going to say that, look, what I'm going to do is I'm going to take this A22, okay, and I will use this A22 to remove this entry by multiplying it. Okay, so what I'll do is I'm going to multiply this row to the one above by dividing it with 1 by A22, okay, times minus A12 and add it. Okay, what will this do? It will produce a new matrix, and we know that we can do this without changing the determinant, right? That was one of the previous properties. You can add subtract rows with coefficients. Okay, so therefore the determinant stays the same, and I have A11 0, A22, and so on, okay, A1 and A2n, A2 A. Okay, so now you have A33 and potentially A13 and A3 would be, should just go up there. So 2, 3 and 3, 6. So I was wondering if I needed this as a minute. Okay, this is A. Right? So what have we done? We have removed one entry from this. So up till now it's basically diagonal. Okay? And now what you can do is you can use the same trick. So you can use A33 to remove. So what do? We multiply with minus A23 divided by A33, right? And add it, correct? Making sense? And what would we multiply here for the first one? Tell me. We want to use this row and add it to the first row. So we want to add the thing, right? So minus A13 upon A33. Okay. Right? So what we are doing is we are taking the third row, we are multiplying it by this number. When you do this, this entry of the third row becomes what? Minus A13. Right? And if you add it to A13, it will disappear. Okay, similarly, so you can make this one disappear, you can make this one disappear without changing the determinant. Correct?
Then A1 is the updated A1, right? After we subtract the second row and the first row.
Yeah, this is updated, you're right. Yeah, so let's call these primes. Okay, that is a good point. So he was saying that, we had A22 to begin with. Oh, sorry, the first row. My mistake. So we changed the first row, right? It's no longer the same as what it was before because we added, subtracted something. So in the first step, right, we changed A11 to A11 minus A12 upon A22 and so on. Times A1, A2, whatever the coefficient, doesn't matter. The important thing is that you will have something which is potentially non-zero and you can remove all the ones. So it's essentially row reduction. And then in the end, you will be left with something which is, crucially, okay, important point. Is A11 prime the same as A11? Question. Why? The ones below 0. So what does that mean? It's leaving the diagonals unchanged. This process, okay? So A11 actually stays the same. Similarly, A22 prime, double prime will be the same as A22, whatever, okay? So the diagonal entries stay invariant under this operation, under these operations, okay? So in the end, you will be left with A11, A22, and all the way to A and N, while all of these other entries will become 0. Okay, so this is 0. That is true. Okay, that part I'll leave in the text, so you can check. Okay, that is an important point. We are dividing by something, so we should check that it's non-zero. Okay? So that part I'm going to leave. You can check in the notes. Okay, that's an important point. Okay, so homework. What happens? I don't even know if I covered it in the notes. I think we did cover it, but anyway. But you get the idea of the proof, right? I think it's very similar to how it's handled in the other cases. So what happens is a diagonal entry is 0. Okay. Hmm. Yeah, I think if one of the entries is 0, then you can just take a linear combination or something. I forget. Something like that. We'll see. Okay. I don't want to spend too much time on this. One can figure it out. Okay. All right. Okay. So those are the 5 properties. Okay, so let's quickly summarize the 5 properties because we're going to use them. So we said that the determinant disappears if any 2 rows are equal. Okay, that's one point. Second is if A has a 0 row, then the determinant disappears. This was also coming from linearity. Okay, the second property. The third was if the rows of A are linearly dependent, then the determinant vanishes. Okay? This was again coming from linear dependence. Okay, and the last property was if you have an upper triangular or a diagonal matrix, in both cases the determinant is just the product of the diagonal matrix. Okay? Right. And there's this question, I may have messed it up because I typeset these things based on Gowtham's notes, I may have messed some things up. Okay, so don't treat this as a finished product. So there are gaps in the argument we can check. Okay, right. So now, so now this is the part where we're going to find the. Let's just do it in general. So so this section is basically trying to derive the formula for the determinant. Using determinant for the end for the 2 cross 2 case. Okay. So it will start with the axioms and it will derive the formula for the 2 cross 2 case. What we will do in the class is we'll do in the general case. Okay, normally we'll do the other, we'll do some examples and leave the proof, but the proof is actually simple. Okay, ready? So let's do it. Okay, so to give the general proof, actually, you know what? I'll give you the 2 cross 2 example. I think that would actually help. Okay, so let's look at the 2 cross 2 example. So 2 cross 2 example is saying that we have A, B, C, D. Okay, so we want to compute this determinant, some general matrix. What we are going to do is we are going to use linearity and split it as follows: plus 0 B, C, D. So why are the determinants the same? Because if I sum this row and that row, I get this matrix. Right? And the linearity of determinants said what? That you can do this. Okay, note I'm not doing it for 2 matrices, I'm just doing it for a row. This is very important. This is not true. Determinant of A is not equal to in general determinant of A plus B, right? Is not in general equal to determinant of A plus determinant of B. Here I'm not doing this, I'm doing it for a row. Okay, I'm not doing it for the entire matrix. I'm just emphasizing it. Is the distinction clear? Okay. And now I can do the same step again, right? I can apply something similar to so how will I apply to this C and D row? So say for this term. So I have A0, what can I write it as? Write it as the same idea. You can write it as what? C0 plus A0, 0T. I can apply the same idea, right? That's right. And I can do it again for this one. So what should I write over here? 0B. Maybe 0T plus 0B. C0. Right? You can do that. Which is the same idea. Yeah? Okay, so now what do we have? Now it's become very nice. Right? It has become very nice because observe that you have exactly one non-zero entry in every row. Okay? So observe one non-zero entry in every row. Correct? And you can always do this. Even if the matrix is big, you can decompose it like this. That you can keep removing the coefficients, and in the end, you can get it into a sum of matrices such that each row has exactly one non-zero. Is that good? Okay. Now, what can you say about this matrix? What is the determinant in this matrix? Yeah. Only using the axioms we have. Don't use extra properties. That is a consequence. We'll prove that. But using the axioms, what can you say about this? So you can use the fact that they're scaling, right? So what can you say about this?
And take A and C common.
Exactly. Exactly. Okay, so remember we can pull out A and this is fine because it's just a linear combination of those. We can also write A times C and then I will have 1, 1. Okay. Okay, now which property have I hit? That two rows are identical. So it's 0. Yeah? Is that fine? Making sense? Okay, and then I can do it for any time two rows. So okay, there are two properties. One is that every row has only one non-zero entry. Okay. The moment any two rows have the same column which is non-zero, then that will vanish. Okay. So that is one observation. And anytime two rows have same non-zero column, right? Same non-zero column. That term becomes 0. Is that okay? So these are just the two properties that we use to derive the entire formula in the general case. Okay, so let's do it for this case. In this case at least, what can we say now? So which terms vanish? So let's call this term 1, let's call this term 2, let's call this term 3, let's call this term 4. Okay. So which term vanishes? Term 1 vanishes, which we just proved. So 1 is 0. Okay. Plus, which one is 0? Third is 0. Okay. What are you left with? Oh, is third 0? Ah, it is 0. Okay. So what are we left with? A, D, 0, 0. Plus 0, B, C, 0. Is this fine? Okay. Is this okay? Yeah? Okay? Alright. Now, how do we proceed? We still need the formula for this. So we already said that for diagonal matrix, we had a formula, right? What was the formula for the diagonal matrix? It was AD, right? Now this one is not diagonal, but we can solve it. Exactly. So now here the crucial thing is, so look, all the non-zero terms meaning the ones that contribute non-zero to the final sum. Okay? So all the non-zero terms have every row with distinct non-zero columns. Correct? Because otherwise they would become 0. Okay? So each row has a non-zero column in a different location, which basically means it's just a permutation of the rows to make a diagonal. Okay, so this implies there exists a permutation of the rows to make a diagonal. Is that okay? So suppose you have like anything like 0, 0, 1, 0, 0, right? You can always permute it. Making sense? Okay. So if you permute it, you'll become minus, and then you'll get C. Is that okay? So we've derived the formula just using the axioms, and nothing else. And this is a very generalizable approach. It's not like we're doing it for one specific instance. You can take any matrix, decompose it like we did, make all the rows have only one non-zero entry, observe that anytime two rows have the same non-zero column, that determinant will disappear. The only ones that would contribute are the ones where the non-zero entries are at different locations. Okay? And then for such matrices, the determinant is just the product of those values times some sign. Okay, and the sign will depend on how many times you have to solve. Like commute. Making sense? Okay. Is this clear? Alright, so let's now write down the general argument. Okay, so for the general argument, we will need some notation. I guess you are already familiar with this, right? It's an example. So permutation on 1, 2, 3 is written as 1, 3, 2, for example. What this means is that sigma of 1 is 1, sigma of 2 is 3, and sigma of 3 is 2. This is just notation. Making sense? Okay, this is just standard notation. Nothing very fancy has been done. Okay, and right. And there's a very nice property about permutations. So what we're going to do is we're going to denote by n sigma the number of pairwise exchanges needed to transform sigma into 1, 2, 3. 1, 2, 3 is the identity. Yeah. So okay, so sigma 1, 2, 3. What does this mean? It's identity, right? Because sigma of 1 is 1, sigma of 2 is 2, and sigma of 3 is 3. Okay, so it's saying that if you start with a permutation, how many swap operations or pairwise exchanges do you need to get it back to identity? Okay, that is the number of. Intuitively, it's just the number of swaps you're doing. That's it. For any specific operation. The interesting thing is that it's not clear that this number is unique, right? Like I could do 2 swaps just for no reason, right? And increase the number, right? So for example, if I wanted to do this, right? So if I had 0, 1, 1, 0, I could, transform this into, and I wanted to transform it into 1, 0, 0. Okay, let's actually make it B and it's a good one. Okay, suppose this is what you wanted to do. I could do unnecessary swaps, right? I could swap row 1 and row 2, and then I could do the same swap again, and then I could do it again. So if I do it 3 times, then it will come back, right? But I could do it any odd number of times, it would still give the same answer. Okay, so the important part is not what this number is exactly. The important part is how many times you have to do that permutation, the number of swaps, and that is called the sign of the permutation, which is 1 if n sigma, the number of permutations you needed, number of permutations you needed to implement number of swaps you needed to implement the permutation. If that is even, that is, if it's odd, it's 1, if it's even, it's 0. Is this clear? Okay, and you can see why it's useful, right? Because in the determinant, that is what we care about. We care about how many times rows and columns, not rows have to be exchanged, right? Okay, so let's look at then what the formula should be. So maybe one nice thing we can already say is that, right, so we wrote down the determinant of A. So what we did was, so we had, your A, whose is this? Somebody's notifications are popping up here, please. Okay, so A, B, C, D, right? This determinant set was what? It was AD minus BC, correct? But what you can think of this as is, so let's write it more systematically. So if we wrote it as A11, A12, A21, A22, right? Then this is basically saying that you're going to look at, okay. Let's not do this. I think it will become easier in the general case. I was going to write the special instance and then show you that how it generalizes, but let's just do the general thing. I think we have enough of it. Okay. So this is the formula. Okay. This is what we're going to prove. So the claim is, or the theorem is, that let det be as in definition 1. Okay. Definition 1. Then det for A, where this is n cross n, okay, is given by the following. It's given by sum over all permutations. Okay, this is permutations on the set 1 to n. Okay, so what you're going to do is you're going to sum over all permutations, and this matrix I'm writing as the ij of the entry of this I'm writing as aij, little aij. Okay. So the determinant is going to be what? It is going to be A1 sigma 1, A2 sigma 2, and so on, all the way to An sigma n sign of permutation. Okay, what is this doing? So okay, fine. Let's look at our example. So in our example, let's apply this. Okay, so in our example, let's apply this argument. So this would be the same as. So, okay, what are the permutations of 1, 2? Okay, so the one permutation is that you do nothing, right? You send 1 to 1 and 2 to 2. So this is a sigma 1, and sigma 2 would be that you swap them, right? You send 2 to 1, 1 to 2. There are no other permutations for 2 elements, right? This is fine? Okay. So now what this means is that I'm going to write So I'm going to apply this formula, okay? And we'll see that it recovers what we wanted, and then we'll derive it. So here we're going to say what? We're going to say that A1. So what was the actual formula? It was A11, A22 minus A12, A21. Correct? That was the formula, right? This you all know now. Now one can write it as follows. One can say that I am writing A1 sigma 1 of 1, A2 sigma 2 of 2, sigma 1 of 2. So the first permutation acting on the second index. Correct? Reasonable? Okay. And then I will multiply, and then I will do minus A1 sigma 2 1 2 and A2 sigma 2 1. Reasonable? Oh no, what did you do? Sigma 2 1 1. Is this making sense? Yeah. Okay. So let's just take a look. So this step is clear, right? This is just recall. This we already know. Okay. I am rewriting it using permutations. Why am I using permutations? Because remember the crucial thing, how did we get this minus sign? It was based on how many times you have to invert the rows. Correct? Okay. So that is what I'm trying to capture now. So I'm saying that for the first one, for this A11, A22, right? These terms, A11, A22 appeared when we didn't have to do any permutation. It moved all the other terms and this was just on the diagonal. All the other terms had been moved. So the determinant was just the product. Right? For the other term, so this is coming from this one, right? It's coming from A11, A22. Correct? This one is coming from A12, A21. Correct? So to compute this determinant, you have to swap the rows. Right? And how did you have to swap the rows? So this is basically capturing the exact same thing. Okay, so you're writing A1. So the first term, right, one can just write it as A1 sigma 1 1, A2 sigma 2 sigma 1 2, where sigma 1 is just the identity permutation. Okay, this is the identity permutation. Is this step clear? Okay, and in the second one, because you have to swap a row, we'll see the proof. Okay, we'll see the proof. I'm just showing you that the formula works. That's all I'm doing. In the second one, sigma 2 is what the second permutation. The second permutation does what? It sends 1 to 2. So sigma 2 of 1 is 2, and sigma 2 of 2 is 1. Right? So if you substitute this, you get exactly the same expression. Right? Yeah? Okay? You get the same expression? Alright. Now what we do is, there's still this sign, right, that is not very clear what the sign should be. The formula says what? It says that the sign is just going to be sign of sigma, of the permutation itself. Okay? So instead of this plus, what we do is we'll write it as A1 sigma 1 1, A2 sigma 1 2. Okay? And here we take the sign, so it would be sign of sigma. Okay? Sign of sigma 1. Sign of sigma 1, identity, no permutation needed. So what is sign of sigma 1? Plus. It is just plus. This is just plus. And then plus, sign of what? What should I put here? I'm applying this formula, right? So it will be sign of sigma 2. Yes. Where are you getting lost? Tell me. Sigma notation? Okay, just a second. So let's see. So the sigma notation is just the following. Okay, so sigma notation is saying that sigma is basically nothing. Okay, it's just a permutation on say n elements. That is all. Okay. So suppose your permutation was that you'll send 1 to 2, 2 to 3, and 3 to 1. Okay. So when I write sigma equals this, it means that 1 is sent to 2. This is not it. This is implicit. So it just means 1 is sent to 2, 2 is sent to 3, 3 is sent to 2. That is it. This way? Okay. And then sign of sigma is just saying how many times you have to permute the rows. Or not the rows, permute the elements. Okay, how many swaps do you need to get the... Okay. So that is the sign. And that's the... So now what we're doing is we're just saying that instead of writing the formula directly here, as we had learned, we'll write it in a more generalizable way. And the more generalizable way of writing it is the following. So we have A1, so the first index stays the same and the second index acts under the permutation. That's it. It's very simple. There's really nothing happening. So the first index as it is, second index under the commutation, and you multiply by the sign of the commutation. That is all we are doing. We are not doing anything complicated. Okay, so then it would be A1 sigma 2 of 1 times A2 sigma 2 of 2. And what was sigma 2? Sigma 2 was defined as 2, 1, right? So it's sigma 2 of, it's swapping basically. So sigma 2 of 1 gives you 2, sigma 2 of 2 gives you 1. Remember the notation I just told you? It's just the notation, right? So you can put 1, 2 here if you want. So 1 is mapped to 2, 2 is mapped to 1. Okay? And what is the sign of sigma 2? Because you have to do one swap at least, it's all. So that would give you a minus 1. Making sense? Right? Yeah? Okay, fantastic. Alright. And what the thing is that this is the general thing. Okay, so we did it for 2 cross 2, yes. We checked that the formula works, but it works in general and we'll prove it. Okay, and it's very easy to do. It's really simple. Okay, so let's see how to do it. Okay, so now it says the strategy is again to decompose each row such that it has only one non-zero column. Exactly like we did in the first case. Right, so we took a row and we split them until there was only one non-zero column. So we'll do exactly that. And then we'll argue that essentially all terms are 0 except n factorial terms. Where is the n factorial coming from? So the n factorial is basically saying that, you know, you have a bunch of rows like this, right? So you have 0, 1. I've removed all the scalars. Okay, so so the prefactors are already here, right? Things like this. Now the point is that you have to make sure that no 2 rows have the same column, non-zero. Okay? So once you've chosen so how many choices do you have for the first non-zero column? You have n. How many choices for the next one? Right? Because if you put it at the same, it will contribute to 0. Okay, and then how many are left? N minus 3 and so on. So you'll get n factorial. Clear? So there will only be n factorial non-zero terms when you do the decomposition. So let's do the decomposition. So let's see how it works. It says that suppose, you know, you write your matrix A as we were writing, V1 to Vn. Okay? And each Vi we are going to write as A ith row first column, ith row nth row. This is fine? This is notation, right? This is just writing the matrix. Okay. So now Vi, every row can be written as what? It can be written as Aij, Ej, where Ej is the standard basis. Correct? We can do that. Okay, so this is j going from 1 to n. One can do this completely fine. Okay. Now let's try to write down the determinant. So the determinant of A is determinant of V1 to Vn. This is just notation. Remember, this is what we said. For A, we'll write it as a sequence of rows. This in turn, one can write as the determinant of. So I'm going to substitute for V1 the expansion that I had written out here. Why am I doing this? Because remember, it's linear in rows. So I have to do it for every row one by one. And what is the special thing about Ej? Ej is exactly the vector with only one 1 and everything else 0. Correct? And that's exactly the decomposition we want. Okay? So we're going to write it. So here we would have 1j, Ej, and then V2 and so on, Vn. Correct? I can write this, no problem. Okay? Right. Now what we're going to do is we're going to pull out this A1j term, and j is going from 1 to 1. Why can I pull it out? Axiom 3. Right? It's coming from linearity. Okay? So now we'll have sorry about this. Right. So this is Ej, V2 all the way to V. Is this step okay? Okay? Alright? And obviously there's nothing special about the first one. You can repeat it for all the rows. Right? Yes? Is it okay? So I can repeat it for all rows. If I can do it for the first, I can do the same thing for the second and the third row also. So what is the expression I will get? I will get, let's call it J1. Okay, so this thing we can call J1 because now there will be many J's. Okay, so J1, J2, let me write it. Most ways, we write it as J1 and summation over J2 all the way to summation over Jn. Okay, I will have A1J1, A1J2 all the way to A1Jn. Oh shoot, 2J. and n also. Is this okay? And then ej1 all the way to ejn. I'm just repeating what we did for the first row, but I'm doing it for all the rows, and I'm introducing n indices, j1 to jn, because for each row we are going to have the linear combination. Okay, making sense? Yes. Clear? All good? Okay. All right. So now let's continue. So we have this expression now, and oh, sorry, I forgot to write determinant. Okay, so you have some coefficients, and you have this determinant, and this determinant is exactly the matrices that we looked at before, right? So anytime you have two ones in the same column, it will disappear, and because these are EJs, they will only have one row in every column. Okay, so therefore, even though this sum contains n from the first one, n from the second, and so on, which is n to the n terms, right? Only n factorial terms will be non-zero. Correct? Okay, and what will these terms look like? So these terms would look like something like this, right? So you have 1, 0, 0 somewhere, and then maybe you put a 1 in the third position, whatever, and then maybe you put 1 in the third, whatever position, right? And so on. Basically, something like this. Correct? This is what the terms will look like. And what are these? These are just permutations of the identity, right? Permutations of rows rows E1 to En. Correct? That is all it is. Making sense? Yes. Convinced? Okay? Right. And since that is the case, one can write this determinant as, wait, what have I done here? I actually don't remember this notation. Okay, you're writing the element itself. Right. Okay, so now each non-zero element in EJ1, okay, so EJ1 has some non-zero element somewhere, right, that we can index with a permutation. Okay. So remember, these are the terms, right? So you can index, you can say this is at the first location, this is at the fourth location, this is at the second location. So for each one of these rows, you can index where the non-zero element is appearing. Okay, and that is just going to be a permutation, because otherwise the determinant disappears. Okay, so therefore one can write our expression over here as sum over j1 to jn a1j. Oh, sorry. So you can remove the j's. So you can just put a sum over sigma. Okay, where sigma is the permutation over Sn, okay, all possible permutations, and you have a1 of sigma 1 and a2 of sigma 2 all the way to an of sigma n, correct? And the corresponding entry one can just write as a1 of sigma 1, sorry, e1 of sigma 1 and all the way to en of sigma n, where the permutation is just telling you where the non-zero entry is. Okay? Making sense? It has to be permutation, right? Because otherwise two rows will become two rows will become identical. Okay, so we have this. Now, see, we are very close, right? So we wanted essentially the coefficient is fine, the A's are fine, right? This is very similar to the final answer. What is left is the sign, and the sign is coming from what? Basically a matrix like this, correct? And what is the sign of a matrix like this? This is the number of times you have to permute the matrix. Okay, so therefore this part is just the same as sin in sigma. Okay, so what do we get in the end? We get determinant of matrix A can be written as sum over permutations of n. Okay, determinant, a1 sigma 1 all the way to an sigma n multiplied by the sign of the permutation sigma. Okay, and we did not use any formula, right? We just used those three properties in this entire derivation, which means it's uniquely specified, right? Okay, It's beautiful, no? I mean, it's just it's so simple. Like, it looks so complicated. It's like from the three axioms, it's not at all clear something like this would emerge. But in the end, it's just, it's very, very nice. Okay? All right. Okay. So we can continue then. Yeah, so this is one of the main results that we wanted to discuss today. So now let's continue. Here are some nice things. Okay, so here we are asked to show that, so the claim is that determinant of, oh, by the way, any questions before I move on about this part? It's fine, right? Alright. So here the claim is that determinant of A transpose is the same as the determinant of A. This is not that obvious. It's not clear a priori. It's just a magical properties about the computation. Okay, so I leave this as an exercise. It's just 2 or 3 simple lines. Okay, so this I'm going to leave as a homework exercise. Okay, you can take a look. It's solved as an example. Okay. The next property is this one is kind of nice. Okay, so I'll tell you what the argument is. This is actually proof sketch. It's not a proof. This one says that determinant of AB. You know this formula, right? Determinant of A times determinant of B. We've seen this many times, right? It turns out one way of proving it is the following. So what you can do is you can take D of A comma B. So you define this new function. Okay, define this new function to be the determinant of AB divided by the determinant of B. Okay, and you fix B. Okay. So I can do that. It's a function. There's no penalties. Anyone can define a function. So you define the function. And it turns out the claim is that D A comma B for B fixed satisfies all the axioms, satisfies all the 3 axioms in definition 1. Okay? So it turns out that it has linearity, it has normalization, it has everything in it. Okay? So for example, normalization you can check, right? If you put identity here, it will give you determinant of B by determinant of B. It's row linearity, all these things you can check. You probably follow from the properties of matrices. Okay. So this turns out good. Okay. Now, because of the theorem we just proved, right, D is uniquely specified. Okay. So if D is uniquely specified with A as an argument, this means that this must be the same as determinant of B. Right? B was fixed. I just defined a new function on A and I said it satisfies all the axioms. So therefore, and the axioms uniquely specify function, which is determinant of A. Right? So it's uniquely fixed. Okay, magical, right? It's not obvious why this should happen. Okay, so this is true. And once you have this, then you're done, right? Because now you have determinant of A is the same as determinant of AB divided by determinant of B. So you get it. Okay? Let me read it. Okay, so you get the product. Okay, there are some subtleties about, the denominator being 0, but those I'm going to skip for you. Okay, K, is it making sense? So here the argument was this. So we were saying we wanted to prove this. Okay? This is the thing that we wanted to show. Yeah? And how we did this was as follows. So we said we are going to define a new function d a comma b. Okay, with B fixed, because it's a function of A. So D is a function of A, B is fixed, and the definition is as follows. So the definition is determinant of AB, it's a well-defined matrix, it's a well-defined function, right, divided by determinant of B. Yeah, I'm sorry, I'll just repeat the arguments if people don't follow. Okay? Is that okay? Alright. Now, the interesting claim is that determinant of AB with B fixed, okay, it satisfies all 3 axioms. Okay, this you have to check. Like for example, you can check normalization. You can take A equals identity, right? And then what would you get? You would get determinant of B divided by determinant of B, correct? Which is 1, as it should be. Okay, so check norm. You can check linearity and all the things. Okay, what is the consequence of this? So that implies the determinant of A comma B with B fixed, right? We were viewing it as a function of A. With B fixed, this quantity is nothing but determinant of A. Oh, sorry, not determinant, D. Huh? No, sorry, I messed up. So let me call this the function D. I messed up. Okay, so I'm defining this function. Okay, so define D. I defined this function D, and the claim was that D of A comma B satisfies the properties of a determinant. Okay, and now D A comma B, because it satisfies the properties of the axiom, must be exactly the determinant of A, which we just derived. Right? We said that determinant of A has to be 0. Okay, so now we can substitute this back here, and what will we get? We'll get determinant of so D of A comma B is the same as determinant of A. Okay, and this quantity is already defined to be determinant of AB by determinant of A, or determinant of B. Okay, so you get the problem. Okay, you have to be careful about division by 0 and things like this, but otherwise that's the it. Okay, so it's a very powerful application of the fact that it's unique. Ooh, was that it? All right, nice. So that's all we wanted to cover for. Okay, this is all we wanted to cover for the stuff that is in the syllabus. So maybe I can go through this example that I sort of skipped because it's part of the course. And the remaining stuff, okay, once you're done with the exams and things, you can take a look. There's sort of nice stuff. It's like very, very beautiful things that you don't want to, you don't want to miss out on joy in life. So since you put in so much effort, you can read the reports. Okay. So now maybe also let's see if we can look at example 6 here. So example 6. Let's do. I'm actually trying to decide if I should do the example or if I should tell you more things. Maybe I'll tell you the more things. The example is actually straightforward. Because it's about permutations, you have to convince yourself. Okay, it's not. It'll get ugly if I try to explain it. Because example 6 I'll leave as an exercise, and I'll just tell you a few more. We can talk afterwards because I can't hear you properly, so I don't want to say something wrong. It's about right, like that is one of the intuition that things don't really change that much once you because of the invariance of permutation. You can invoke it in different ways. I was doing it formally. Maybe there's like a simpler way to do it. Okay? So that will leave as an exercise. Let's look at some fun things. Okay, so let's have some the last few minutes. Maybe I should say that if you want to leave or want to do something else, you're free to do it. Okay, because this is not really in the simple. So this is just fun stuff. Okay, so right. So the definition of trace. Let's look at this. So trace is okay. So trace for a matrix A is just the sum of the diagonal entries. Oh yeah. Whose is it? Just whoever's notifications are going off, please just take a minute. Okay. Right. So it's just the sum of the diagonal entries. So not a big deal. Then there's this idea of, so we'll see where it becomes useful. There's this very nice property, okay, this maybe I should mention. So the determinant of exponential of A, okay, so what is exponential of A? Exponential of A is just, so what is the power series for exponentiation? So it's identity plus A squared by 2 factorial plus some, right? That's the, okay. So this is how it's generalized to matrices. You just take the matrix, you take identity plus the matrix plus square, yeah, so, okay. So if you compute this quantity, determinant, this weird quantity, okay, of the exponential, which is like this crazy power series, okay, this it turns out is exactly the same as the exponentiation of the trace of. Okay. This is completely wonky looking, but once you see that it's its product of eigenvalues and sums of eigenvalues, things sort of make sense. Okay, so we'll see. Because by the end of it, once you've read the rest of it, you can come back to this and see that it sort of makes sense. Because you can assume things are diagonal, at least in that case. Because you can assume that consider A is self-adjoint or whatever, then things are diagonal, and the diagonal basis it will be product of eigenvalues, sum of eigenvalues, and exponents. Okay? So it's basically just using this fact that. EB is the same as EA plus B. Okay. So it's going to sort of use this fact. So this is going to be like the, this is product of things. product of exponentials, and this is exponential of sums, right? And the product and sums would be related by determinant and trace. Okay, so that's the point. All right. So now let's quickly see how determinants can be used to find inverses. So here we'll just state the general formula. Okay, so we don't really do the proof here, but this is something you should know since you're taking linear algebra. In case you don't know, so this is the formula. What is C? So C is the following matrix. Okay. So what you do is you compute the matrix M Ij from, so suppose you're given a matrix A, Mij is going to be A with I and J, ith row, so ith row and jth column removed. Okay. So Mij is clear what the definition is? Okay, so you have the matrix A, you remove the ith row, jth column. Okay, so that's Mij. And Cij is defined to be minus 1 I plus j determinant of Mij. So basically what it is saying is you can take your first matrix, remove a bunch of rows and columns, compute its determinant, multiply with some coefficient, okay? That will give you Cij, and this will give you the matrix C. So C11, C12, and so on. Okay, this is the matrix capital C. You take its transpose, divided by the determinant, and magic. You have the inverse. Okay, so we don't have time to prove this, but it's pretty insane where the determinant shows up. Okay? Like there's no business this should go up, but it does. Okay, so that's one thing. Then this other fact is the very, very complicated fact you see that A inverse is the same as A inverse. Okay? So what is it saying? That the left and the right inverse of the matrix have to be identical. I think we already proved something like this in class. The idea is very, very simple. Suppose you had different inverses, call them left and right. So left times identity would be left times identity times R, or A times R, because the right inverse, which you can say is left times A times R, but left times A is the left inverse, so you get it. Okay? So the left and right inverses always have to be the same for matrices. Good? Square matrices. In fact, everything is about square matrices. Okay. Now, right. So now let A be an n cross n matrix. Okay. The lemma says A is invertible if and only if determinant of A is not equal to 0. Very useful property. Okay. So how does the proof go? It says, okay, so you first of all have to have determinant not equal to 0 for the inverse to exist because, well, we can just use the property we proved, right? So determinant of A inverse is determinant of A inverse, right? Which is also equal to determinant of identity, which is 1, right? So these things cannot both be 0. In fact, neither of them can be 0. Otherwise you will be in trouble. Okay? So therefore, A is invertible if and only if the determinant is 1. So it's necessary. Sufficient is because, we have this formula, right? Otherwise the formula won't work. You have a division by 0. Okay, so necessary we already showed and sufficient. Once you have the determinant, you can compute the inverse. So let's set it there. Reasonable? Okay? So that is one nice thing. Now comes the fun part. Okay? This is where the actual magic happens. Now what we're going to do is we're going to relate determinants to eigenvalues. And the trace also to eigenvalues. So the statement is as follows. So we can show that lambda is an eigenvalue of a matrix A if and only if determinant of A minus lambda times identity is 0. Okay. Why is that? Let's try to understand it. It's saying that if you have an eigenvalue, Ax would be lambda x for some x, right? Which means A minus lambda times identity, x is 0, right? Which means this matrix is not invertible, right? And if it's not invertible, we just saw that there's a relation with determinants. Okay? So therefore, basically it's saying that if you have an eigenvalue of lambda, if A has an eigenvalue lambda, then it is equivalent to checking whether determinant of A minus lambda identity is 0. Okay, it has to be 0 for that one. Is that okay? Making sense? Okay? Oh, very good. So now comes a very, very nice theorem. Okay, so this theorem, I don't know how much time we have, maybe not enough. But we'll see how much we can do. But the statement should be clear because the statement says that let A be an n cross n matrix, right? Then we have that trace of A, okay, which is just the sum of the diagonal entries. Is actually not just the sum of the diagonal entries; it is the sum of the eigenvalues. Okay, so let A be a matrix and lambda be the eigenvalues. Lambda 1 to lambda n be the eigenvalues. Okay, so if you have some matrix A, we know that when it's complex, you can always find eigenvalues. Right, we saw that in the previous chapter. In reals, it's not the case, but with complex, you can always find eigenvalues. Remember, this was in chapter 5, I think. Okay, now it's saying that the trace, so if you just sum the diagonal entries of a matrix, regardless of what kind of matrix you have, okay, it will be the sum of the eigenvalues. Okay, of course, the other way is completely trivial. If you have a matrix that is diagonal already, then it's completely trivial. The other direction is the non-trivial part. If you have any matrix, the sum would still be the sum of eigenvalues. Is that okay? Okay, so that is one. The second statement is the following, that the determinant of A, okay, the determinant of A is going to be the product of the eigenvalues. Again, it matches the intuition. If you have a diagonal matrix, can you hear me still? No, of course not. Okay. So if you have a diagonal matrix, the determinant is just the product of the eigenvalues, right? So if you have lambda 1 to lambda n, if these were diagonal, right? These are 0. What is the determinant? We just saw this, right? It was just from, I think, one of the properties that we had written. This lambda 1 to lambda n, right? This is saying that even if you have like some crazy matrix, okay, some complicated matrix, it would still be the same as the product of the eigenvalues. Okay, making sense? Okay, right. So now with this intuition, you can go back and check this crazy formula that we had, right? Like with crazy exponentiations and determinants and whatnot. If you suppose that the matrix is, say self-adjoint, so you can diagonalize it. Okay, what this expression is saying is that you have the determinant of e to the, say lambda 1 to lambda n, okay, be the same as the exponentiation of the trace of A. So trace of lambda 1 to lambda n. Okay, so what would this side give you? It would give you lambda 1 plus lambda n. You have exponentiation of this. That is the right hand side. Yeah. What is the left hand side? The left hand side is basically, this is going to give you the determinant of e to the lambda 1, determinant of e to the lambda 2. Uh-oh, did I mess it up? Okay, I myself messed it up. Okay, so you guys need to go and check. Okay, I think I screwed up a little bit, and I think we have about a few minutes. I don't want to mess things up more. So you take the exponentiation here, and when you evaluate the determinant as just the, oh no, it was fine, right? It was, okay. Let me write this actually. Okay, so this would be, okay, let me fix that. So this quantity here becomes e to the lambda 1. It's diagonal, right? So you can write it as e to the lambda n. Right, it's diagonal. So when you write this expression, the power series, every term is getting squared, cubed individually, right? It's diagonal. There's nothing to do, right? It's just you do it. All right. And then, what is the determinant of a diagonal matrix? It is e to the lambda 1. It's just the product of the eigenvalues or the diagonal entries, right? Lambda 2 all the way to e to the lambda n. Correct? Okay. And then what is this equal to? This actually is equal to that, right? Okay. Can you say numbers a bit? Let me label it. This part 1 to 2. Yeah, 1 to 2 is basically saying the following, right? So if you have e exponentiation of a, let's just apply the formula, right? So e to the a is defined to be what? It's identity plus a square by 2 factorial and so on, right? That's the definition. Okay. Now if a is diagonal, right, what would you get? You would get, 1 plus, what would you get? lambda 1 to lambda n, right, plus lambda 1 by 2 square lambda n by 2 square, right, and so on, correct? And then you sum it, right? So you get it. Okay. So you see, this is like this is absolutely crazy. that something like this would be true. And underlyingly, all it's using is the fact that you just have sums and products. The traces are basically sums and determinants are products. Because that's like one of the nice applications of these things. And that's especially useful when you don't have such clean, like you don't know the eigenvectors, for example. You just have the. Okay. So I think with this we can maybe we can call it today.